This is Anita from VV Vannyaperumal College for Women. In this module, we deal about the deviation from ideal behavior, compressibility factor, and the derivation of the van der Waals equation. In our previous module, we have seen about the Maxwell-Boltzmann distribution of molecular velocity and the different types of velocities and how they are related with each other in case of a gaseous substance. In this module, we have seen how the gaseous deviate from the ideal behavior, how the existence of real gas occurs, and what are the properties of it, and what basis the gases deviate from the ideal behavior, and the reason behind it, and how it can be rectified in the derivation of the van der Waals equation. How? The gases which obey the ideal gas equation, like the PV is equal to nRT, is called as an ideal gas. But in our day-to-day life, no gas is ideal. That is, all gases like what we have seen in our daily life, like nitrogen, oxygen, carbon dioxide, they are all deviate from the ideal behavior, and these gases do not obey the ideal gas equation PV is equal to nRT, and these gases are called as real gases. And these how much the gases deviate from the ideal behavior is given by the compressibility factor. That is, the how much it deviates, that the depart from the ideal behavior is given in terms of the compressibility factor Z is equal to PV divided by RT. If PV equal to RT, then the Z value is equal to 1. If any of these values will be different, then the PV by RT will have either the value greater than 1 or less than 1. The difference between the values, that is between the 1 and the Z value, is given as the deviation of a gas from its ideal behavior. Larger is the deviation, larger is the deviation of the gas from the ideal behavior. Larger the difference, smaller the difference in the value, smaller is the deviation of the gas from the ideal behavior. Therefore, the compressibility factor is the magnitude which tells us how much a gas deviates from its ideal behavior. Now, the deviation happens by changing the two parameters. One is the pressure and the another one is temperature. Now we see about the effect of pressure and the deviation of a gas from the ideal behavior. From here, Z is plotted versus P. That is, the compressibility factor is plotted against the P atmosphere for different gases like nitrogen, hydrogen and carbon dioxide. From this graph, we are having a dotted line which is for the ideal gas. Here the value of Z is 1, that is, the value of PV is equal to RT, then the value of Z will be equal to 1. The dotted line indicates the gas is in ideal behavior. But what we have seen for the nitrogen gas is different from that of the ideal gas behavior. Likewise, for the hydrogen and the carbon dioxide also, the gas deviates from its ideal behavior. If this gases behaves like an ideal, then there will also be a straight line, that is, having Z value equal to 1 for any deviation, for any variation of the pressure. For the nitrogen gas, there will be a decrease in the value, that is, as P increases, the value of Z will decreases from value 1, that is, it has value less than 1. After a particular pressure, the value increases, that is, its value becomes greater than 1. For a hydrogen gas, there will be no negative deviation, only a positive deviation, that is, the value of Z is always greater than 1, whatever the pressure value is. For the gas like carbon dioxide, there will be a huge negative deviation from the ideal behavior at lower pressure. After that, for a particular pressure value, this value, as pressure increases, there will be an increase in the value of Z as P increases. This indicates that if the gas is not easily liquefiable, the presence of straight line will be like this, that is always the positive deviation. If the gas is easily liquefiable like carbon dioxide, then there will be a high negative deviation followed by a positive deviation of Z on increasing the pressure. These are the observations we are getting from this graph. Next to that, we can see what is the effect of temperature on deviation. Here, the Z value is plotted against pressure for the same gas, nitrogen, at different pressures, like at different temperatures like 200 Kelvin, 500 Kelvin and 1000 Kelvin. Here at 1000 Kelvin, there is only a value increase in the value is, the Z value is always greater than 1, whatever the pressure may be. But in case of 500 Kelvin, the value gets negatively deviated. The value becomes less than 1 on increasing pressure for a particular amount of pressure. After that, the value of Z will be greater than 1. For measuring the Z value at 200 Kelvin, at lower pressures, the Z value will be always lower than 1. After a particular pressure, it will becomes greater than 1. Therefore, it will show only the positive deviation. Here there is a light negative deviation. Here that will be a higher negative deviation. As temperature increases, the deviation from the ideal behavior decreases. From this, we have concluded from 2 points. From this graph and the previous graph, at low pressure, the gases behave ideal. Similarly, at high temperature, the gases behave ideally. These two are the conclusions we are get from the compressibility factor. At low pressure and fairly high temperature, nearly all the gases show ideal behavior, or the deviation from the ideal behavior is less. At low temperature and sufficiently high pressure, there will be a huge deviation of the gases from the ideal behavior. At that point, the ideal gas equation is not at all obeyed. Closure is the liquefaction point of a gas, then there will be a larger the deviation from the ideal behavior. If a gas is easily liquefiable, then it will not be an ideal gas, and there will be a huge deviation from the ideal behavior for that particular pressure. Now we can see how the gas deviates from its ideal behavior and what are the reasons behave it. The reason for the deviation, it comes from the previously we have seen about the kinetic theory of gases. At that point, we have seen that there will be a point mass and there will be no intermolecular force of attraction between the two molecules, and these two postulates have shown erroneous limits. Here we have seen the molecules are point mass and possess no volume, and there will no intermolecular force of attraction between the molecules. But how this will be has its effect on the ideal gas equation and its deviation from ideal behavior. Now first we have seen about the volume correction. Here in our ideal gas we have seen calculated this volume as V, but there will be large amount of empty spaces which we have included that also for your calculation. But when all these molecules can be accommodated in a very small volume, the remaining space will be empty. Therefore, the remaining volume which we have included in this volume space is called as the excluded volume. This excluded volume has no effect on the behavior of the gases. The volume originally occupied by the gas is only 1/4 of the volume we have used it for the ideal gas equation. Therefore, we have seen that large amount of empty spaces are there, which will also has its impact on the ideal gas equation. Therefore, the actual volume is less than the volume we have calculated for the ideal equation. So, we have calculated that as V minus B, where B is the excluded volume, that is the empty space, that on subtracting the empty space from this true value, we can get the actual volume occupied by the gases. That is one of the reason for the deviation from the ideal behavior. Next, we can see about the pressure correction. Here, the molecule exerts pressure on all the sides. If the pressure is exerted in the right hand side, it also exerts pressure on the left hand side. Therefore, it gets cancelled with each other or get balanced. Similarly, the upward pressure is balanced by the downward pressure. This is the case when the molecules move. But when the molecules collide with the walls of the container, the pressure are not at all balanced. There will be exist in an inward pull. Therefore, what the pressure exposed by the molecules in the ideal condition and what is in the actual conditions are different from this. That is, the pressure exerted will be lesser than that of it. Actual pressure is less than that of the ideal pressure. Therefore, actual pressure is equal to ideal P ideal minus P. Therefore, P ideal is equal to capital P plus small p. For that, we have considered two molecules it depends upon the concentration of the A and B, where concentration of the gas molecules will be equal to the number of molecules divided by the volume occupied by the gas. Therefore, we have get n square divided by V square. The P is proportional to n squared V square. To remove the proportionality, we have multiplied by the van der Waals constant A. Therefore, the pressure should be added, the pressure correction should be added with the ideal pressure in order to get the real term pressure. With these inclusions, that is the pressure correction term plus the volume correction term can be included and it is replaced for the P terms and the V terms, then we can calculate it for the ideal gas equation. It is simply the ideal gas equation, but we are included the pressure correction factor of A n square divided by V square, that is added to the pressure term, and the excluded volume is subtracted from the volume term in order to get the van der Waals equation. Here it is P div plus A by V square, and V minus NB is equal to RT is the van der Waals equation for 1 mole of a gas. For a n mole of the gas, the previous equation, that is P plus A n square divided by V square, V minus NB is equal to RT is the van der Waals equation. From this video, we can see how there will be a deviation from the ideal behavior and what are the reasons and what are the conditions at which the pressure is deviated from the gas is deviated from the ideal behavior and how it is rectified that leads to the birth of the van der Waals equation. In the next class, we will see about how the van der Waals equations are used in our daily life. Thank you.